All right, well, we've seen Devitt's arguments, right, against the one over many argument for Platonism. Then we've seen Quine's arguments, which are basically the same. Devitt is just sort of recounting Quine's arguments. But when we finished with Quine, it turned out that we might have to be committed to the existence of numbers as abstract objects if they feature in our best scientific theories, right? Again, um, Quine says, what exists will just depend on our best theory, that is the simplest theory, right? So you could make a scientific theory that only talked about sensory information. That's all we have immediately, right? We don't have direct access to physical objects. Um, but it's a much simpler, more elegant theory if we posit that physical objects exist. And likewise, it's a much simpler, more elegant theory if we posit that numbers exist. So we should accept that numbers exist. Um, So, yeah, phrase like that, I don't know that there's ultimately a real contradiction between Field and Quine, right? Field is going to say we can do science without numbers. It'll just be a bit more complicated. And that's sort of what Quine is saying too, but Quine is saying, well, if it's more complicated, then that's worse, right? But, that's sort of an open question, right? We've been assuming this whole time that we should accept the simpler theory as true, but there's no good reason for why that should be the case. It might be the case that nature is complicated. It's sort of an aesthetic criterion. I mean, it dates back, right, to William of Ockham, Occam's razor, says accept the simpler theory. And in practice, in science, we tend to, yeah, favor the simpler theory. Um, but it's not entirely clear why, right? Humans like to do that. So anyways, Field's going to show us how we could, if we wanted to, do science without numbers, right? And just showing that, contrary to what Quine says, we can believe in the truth of science without believing that numbers. So again, recall Quine's criterion of ontological commitment, right? He says we are committed to the existence of those entities that appear as bound variables in the senses we believe to be true. And in the last lecture, I explained what that meant, a bound variable. It's a little bit of logic world, but not too tricky. Um, so if we think scientific statements are true, right? And if when we translate those scientific statements into logic language, if, for example, if numbers appear as singular terms, then it looks like we're committed to the existence of numbers. Um, or if science is just committed to the truth of mathematics in general, right? Then there are certainly sentences in mathematics, like 3 is prime, that seem to feature numbers as singular terms. And so we're committed to the existence of numbers. And, you know, we'll see, like, uh, it seems like the next question is, well, what is a number then, right? Does it have to be an abstract object? Maybe numbers are just mental objects, right? Maybe they're just ideas. But we've seen that, because numbers are so infinite, uncountably infinite, that even though there's a lot of ideas out there in the world and a lot of brains, maybe even alien brains, who knows, it's not uncountably infinite. So there's going to be more numbers than there are ideas. So numbers can't be ideas. Um, Quine just sort of assumes that numbers aren't physical things, and we're going to see in the next reading that Penelope Maddy will argue that no, numbers actually are physical things. In which case we can accept Quine's criterion, we can accept it through the science, and we don't have to believe in abstract objects because numbers are just physical, right? Um, but Field is intervening at another point, and he's saying, well, we're only committed to the existence of numbers if we think that mathematical statements are true. Right? If we think that 3 is prime is true. But he's going to say maybe 3 is prime is not true, right? Now, the thing we were worried about is like, well, don't we need it to be true that 3 is prime in order to do science? And we really need science, right? That's pretty important. And we want science to be true. Uh, and Field is going to say, no, we can keep science and give up on numbers as being true, right? So what would that mean? Well, he says, look, what really matters in mathematics is not that mathematical sentences be true is that they're all consistent, right? So think about like, reading a novel or something. Um, nothing that happens in the novel is true, but it can still be internally consistent and that it all makes sense and there's no contradictions within the novel, right? Um, and Field wants to say something like that. Look, mathematics is a story that's internally consistent. It's very useful, right? We can use it to make science easier, um, but we can separate it out from science, right? So that science can be true and math can be a useful fiction. So we're not reading his whole book, right? The whole point of his book is to sort of show how we can formulate, right? All our best scientific theories can be sort of retranslated, reformulated without using numbers. Um, so that, we don't have to say things like the acceleration of gravity on Earth is 9.81 meters per second squared. We can say something else that doesn't have the number 9.81 in it, right? Um, Obviously, that's going to be a long, complicated thing. It's a whole book. Um, I'm just going to get to the point where you can understand the principles behind it and understand how that project will look, right? And if you want to read the book on your own, feel free, right? So the passage we've read, it's a little tricky, um, these passages, but they're from basically the introduction, some selected passages from the book. So here's a good point to where we can sort of start to flesh out a taxonomy of different varieties of nominalism. Remember, Platonists are people that believe that abstract objects exist. Nominalists are people that believe that abstract objects do not exist. And there's different types of nominalism. So Field is a nominalist. He doesn't believe in abstract objects. He's what we call a fictionalist, right? So he says that sentences that refer to abstract objects are just not true, right? So 3 is prime seems to use 3 as a singular term, and it's not true. It's actually a sort of a false sentence. False in the way that, right, David Copperfield is clever is false, right? It's kind of true within the story of the Dickens novel, but strictly speaking, it's false because David Copperfield does not exist. So that's one kind of nominalist, fictionalist. He says, right, mathematical statements are fiction. Physicalists, which is Penelope Matty, who we'll read next, she says, well, no, 3 is prime is true, right? There's a singular term in there. 3 features a singular term. We're committed to its existence, but 3 is a physical object, right? It's a sentence about physical objects, not an abstract object. And then another philosopher, Jody Azuni, who we won't be able to get to, but just to know that there's even more approaches to nominalism, he will say, yes, sentences like 3 is prime are true, but they don't need to refer to anything in the world to be true, right? So he says, if I say Santa wears a red hat, that's a true statement, even though Santa doesn't exist. So he just rejects Quine's criterion altogether, that we are not committed to the existence of things that feature as singular terms in statements that we take to be true. Right? But we won't get into that approach very much. So everyone we're reading accepts Quine's criterion, right? Nooney is the only person I know that. Okay, so uh, when Field was writing, fictionalism was not a popular approach to nominalism, um, because if you think that scientific statements require the truth of mathematics, we all would like scientific statements to be true, right? We don't want to necessarily deny their truth, right? We want it to, science is our best approach, our best method of knowing things about the world, and so we'd like it true. And so people thought, well, if we don't want to give up on science, we better believe that numbers exist. That's what Quine said, right? But Field's strategy is going to be, no, we can keep science because we can reformulate, we can rephrase all the scientific statements in a way that doesn't mention numbers at all. So that way we can cordon off the mathematical statements, right, that are false from the other statements that we'd like to say are true. So this is not, strictly speaking, a positive argument for nominalism, right? Instead, he's defending nominalism against Quine's argument. Well, if we want to believe in science, we better believe in numbers as abstract objects, right? But that's really all he needs to do, because I think most people would say the default would be to not want to believe in abstract objects unless we have to, right? It's this extra realm of existence. Again, it makes our ontology kind of messy, right? It'd be nice if we could get away with just like, yeah, look, there's physical objects and that's it. So sort of the default for most people would be nominalism. And so Field is just trying to preserve that by um, blocking Quine's argument that we need to believe. Okay, so how's this approach going to be? First, Field distinguishes between mathematical and theoretical entities. So mathematics is obviously useful for science, right? And for Quine, that counts towards their existence, right? If it's useful for our best scientific theories, then yeah, sure, we'll commit to their existence, right? And Quine mentions things like superposed electrons, right? Some of the weirder stuff that comes up in quantum mechanics that seems to violate like laws of logic. He says, hey, if it helps us with science, if it's useful for science, then yeah, we'll believe in superposed electrons and we'll get rid of that law of logic. Fine, right? But Field wants to say Quine is sort of lumping together, right, things like um, superposed electrons and numbers as if they're the same sort of thing. He wants to say, no, they're both useful, but they're different types of things. They're posits, right? So no one's ever seen a superposed electron. We're positing that it exists, right? But we're positing it because it plays a role in the theory, right? And it makes predictions. Um, he says stuff like electrons and stuff like numbers, different types of things, useful in different ways, right? And so they can be kind of carved. So yeah, in science, we posit the existence of all sorts of things we can't observe, right? Because they play a role in the theory. It makes sense of the phenomena. It makes true predictions, right? It makes sense of what we um, electromagnetic fields. You can't see them, right? But they make sense of the behavior of magnets and why you can create a current in a wire by moving a magnet and so on, right? It makes true predictions. So when do we accept a theoretical entity, right? When do we accept the existence of electromagnetic fields, even though we can't see them with our eyes? When do we accept the existence of superposed electrons, even though we can't see them with our eyes and they seem to violate the laws of logic? Well, A, do they play a role in a powerful theory, right, from which we can deduce a wide range of phenomena? It makes a lot of true predictions. And then B, is there not another theory that makes the same sorts of predictions, right, as explanatorily useful? Um, those are the two times that we accept things that we can't see, right? But we say these things exist. Um, and so long as they satisfy A and B for Field, that's fine, right? Uh, that's a good reason to believe those things exist. But mathematical entities do something completely different, according to Field. So again, a theory of subatomic particles, we can't see them, but it allows us to make predictions about things we can see that we wouldn't otherwise be able to explain. Whereas a theory of mathematical objects doesn't actually make any new predictions about things that we can observe, or at least any predictions about things we can observe that we couldn't have made without the mathematics. And part of his project would be to show that that's the case. Right? A lot slower when you don't use mathematics, but you could still, according to Field, make the same predictions. Right? Um, so why is this the case? Why does mathematics not give us any observable predictions of things that are observable? Because mathematics is a priori, right? By a priori, we mean doesn't require observation, right? We can figure it out completely in our head. Um, it doesn't depend on the world at all for its truth, right? 2 plus 2 is 4. Doesn't, right? There's nothing in the world you're going to observe that will prove the truth of 2 plus 2 equals 4. It's proved completely on the mathematical plane, right? Um, so if math adds anything to our knowledge about the world, it's only stuff that was already logically true, right? Um, so adding math to our knowledge of the world can't make any new predictions about the world. Now, it'll make making predictions more convenient, right? Mathematics is very useful, but mathematics is not adding new information, right? Um, this is what he calls the conservativeness of mathematics. It's consistent, right, and useful, but it doesn't add to our empirical knowledge. Um, knowing that 2 plus 2 equal 4 does not tell you anything new about the physical world. Theoretical posits, on the other hand, are not conservative. They add to our empirical knowledge, right? So um, the fact that there are electrons or electromagnetic fields, right, that's a new thing in the world that we've posited, right? Mathematics is not a new thing in the world, right? Okay. So if that's true, right, and they're separate, math is not about the world, right? Um, we can use math when we're talking about the world, but that doesn't necessarily mean that those mathematical statements have to be true to make our statements about the world true. That's because mathematical statements are truth preserving, right? We can use math in science, even though it has nothing to do with the physical world, because it's internally consistent. It's never going to introduce falsehood. Right? Take information about the world, right? Use mathematics, and mathematics is never going to take a true premise and spit out a false conclusion, right? Mathematics will always take in truth and spit out truth because it's internally consistent. But that being internally consistent is not the same as being true, right? So imagine that you have a friend who believes in conspiracy theories, right? You can still make predictions about what your friend will do as long as his conspiracy theory is internally consistent. So if he has some, right, conspiracy theory about vaccines causing autism or whatever, you could predict his behavior, right? He's probably not going to take a vaccine. He's probably not going to give his kids vaccines. Now, his theory is false, but it's still useful as long as it's consistent, right? And same with math. Math doesn't have to be true to be useful because it's consistent, right? Because if you feed in truths, it will spit out truths. Now, if you feed in falsehoods, it might spit out falsehoods, right? But it is truth preserving as long as you feed in truth. So, yeah, math is not going to introduce any falsehoods into our scientific theories, right? Um, okay, but then why? But still, that's not enough to want to use it. Well, it's also useful to use it, right? So it's safe to use it. It's not going to turn any of our statements false, but also it makes things a lot faster, right? So he says call n a scientific theory that doesn't mention abstract objects, and then call n plus s a scientific theory that includes a mathematical system. And let's say that anything we can say in n plus s, we could also say in n alone, right? It would probably just take a lot longer, right? Um, well, if again, if n plus s speeds things up, makes things quicker and easier, then yeah, let's use n plus s, right? It's not going to introduce any falsehoods, and it's going to make our lives easier, right? So, for example, suppose we want to determine whether this inference is valid. So there are, premise one, there are exactly 21 aardvarks. Premise two, on each aardvark, there are exactly 3 bugs. And number 3, each bug is on exactly 1 aardvark. Question, and the conclusion we want to draw is there are exactly 63 bugs, right? Um, which is just, 21 times 3. Now, we can do this without math. Right? We don't have to have numbers featuring a singular term, but it's just a real pain in the butt. So to make it even slightly easier than it actually would be, Field introduces a quantifier called exist nx, which is like where n is some number. That sort of sounds like he's committing to the existence of numbers, but it's not cheating. We can do the whole thing without that special quantifier. I'll show you how. It's just super long and clunky. So if you've taken a predicate logic class, this should look familiar. If you haven't, it should be fairly straightforward. So if I want to say there are at least 2 bugs, so 2 is a number, but in logic language, I can say that without any numbers, and it would be this: exists an x, exists a y, such that bx and by, and not the case that x equals y. What does that mean? That means there exists an x and a y, so there exist 2 things, and bx means x is a bug, by means y is a bug, and x and y are not identical, right? So they're distinct things. I just said there are 2 bugs without using the number 2, right? You can use the same strategy to say there are 3 bugs, there are 4 bugs, up to 27 bugs, however many you like, right? You can imagine how long the sentence in logic language is going to be, but yeah, you can talk about, right, groups of things without using numbers. It's a slightly less clunky when you use Field's sort of made up number quantifier, but it doesn't really change anything. Um, so imagine how much easier it is, right, to just say 21 times 3, right? It's like 2 steps instead of God knows how many steps to make that inference, how long the sentences have to be in logic. But again, the mathematics isn't adding anything except simplicity, right? It's not going to introduce any falsehoods. It's consistent, and it's just useful. It just makes things faster, right? It doesn't have to be true to do that. So let's look at geometry, which is another way to understand how we can sort of separate numbers. Um, so this idea of ascending from n, which is again a theory that doesn't talk about numbers, to a theory that has numbers in it, solve some sort of problem, right? Make some sort of derivation, and then move back down into n. Uh, it can be extended to geometry, and you certainly want geometry if you're going to nominalize physics. You're going to make physics without numbers. So the reason we can do this is because of a homomorphism. So when two things are homomorphic, it means they have the same structure. So maps are a good example of this. A map is homomorphic with a certain physical space. So here's a map of the UCSD campus, right? It's obviously much smaller than the UCSD campus, right? But it preserves many of the same relations that physical items have, right? It preserves part of the structure of the campus in this much smaller format. And so that helps me to make inferences about the actual physical campus, right? So, for example, if I want to know which way I need to leave from this building to reach my next appointment in the shortest amount of time, I can look at the map, calculate the angle. It's going to be the same angle in physical space. So, if you can create an abstract structure using abstract objects that is homomorphic to the structure of some set of physical objects, like what a map does, then you can perform the operations on the abstract structure, draw conclusions, and you know that your conclusions will be good in actual space. Field wants to show, as an example, that Hilbert's formulation of Euclidean geometry is one example of this. So Euclidean geometry is geometry that assumes that parallel lines never touch, which is an assumption if space is flat, right? But it's that assumption is violated in like a sort of a sphere, right? There's non-Euclidean geometries out there. So Euclidean geometry isn't really true, strictly speaking. It's sort of a subset of a broader geometry, but it's a helpful example, right? Um, because Hilbert's formulation of Euclidean geometry doesn't use numbers at all. So there are a few basic predicates in Hilbert's geometry, and none of them are numbers. So there's is a point, right? So it defines things as points. It defines a betweenness relationship, a congruent segment relationship, and a congruent angle relationship. So congruent, just means same size as, right? But it's saying same size as without using numbers. Right? And Hilbert also proved that his system can be mapped onto the real numbers, right? So you can use real numbers in calculations, exactly like as Field says. You can start with n, do n plus s, do some calculations, and come back, and it won't introduce any falsehoods, and it'll whatever conclusion you draw will be true in n as well. Um, so, for example, right, one of the important ways that Hilbert's geometry can be mapped onto the real numbers is that distance relations will remain constant when multiplied by real numbers. So if you have two line segments, A and B, and say you want to say that B is twice as big as A. Well, the way you would say that without numbers is that B concatenated with itself is congruent with A. That's saying A equals 2B, but without numbers, right? And if you ascend into a world that has real numbers and multiply both of those times 6, that relation will stay the same, right? B concatenated with itself will still be congruent with it. So this example from geometry is just one example of how you can have these two systems, one that doesn't use numbers, and you can add numbers, but it doesn't introduce false heads. So Hilbert's geometry only talks about spaces, right, which the nominalist believes in, but it can be mapped onto the positive real numbers. And so we can ascend to a system that includes those numbers in order to simplify our calculations, then descend back into the system that only talks about spaces, and no falsehoods will have been introduced, and the two systems can be kept separate in principle. One can be true if you like, and the other doesn't have to necessarily be true, so long as it's consistent. Here's another example, right? So we have two triangles that form right angles. It's a little hard to see in this copy, but A1, A2, A3, and then B1, B2, B3. So suppose that A1, A2 is twice as long as CD. Now, of course, you can say that without numbers, right? You can say something like there's a point X between A1 and A2 such that A1X is congruent with CD and A2X is congruent with CD, right? And if we also say that A2, A3 is 5 times CD, and B1, B2 is 3 times CD, and B2, B3 is 4 times CD, again, but without the numbers, right? It'd just be concatenated with. Now you might want to know, is 1A3 longer than B1, B3? Do it without the numbers, right? But it sure would be easier to ascend to n plus s, right? And use the Pythagorean theorem, and then get your answer and descend. So again, point being, you don't need to assume the truth of the number theory, right? Just that it's conservative, it'll do its job. So one objection that someone who's familiar with Hilbert's geometry might pose is that he describes space as uncountably infinite, just like the real number. So meaning that, right, any piece of segment of space can be divided over and over and over and over and over, right? So does that mean that his space essentially is the real numbers, right? Are they basically equivalent? And Field wants to say, no, they're not equivalent, right? So the difference is real numbers are abstract entities and space is physical, right? So if space, this physical thing, turns out to be divisible infinitely, that's fine, right? That doesn't mean that you're committed to abstract objects. You're just committed to space still, just a particular kind of space that you can want, right? Sort of an empirical question whether space is uncountably infinite, and whether the real numbers are uncountably infinite is not an empirical question, right? That's something in mathematical theory that's completely a priori, right? No observation would tell us whether the real numbers are uncountably infinite. But some physicists, this is a live question in science, right? Because in quantum mechanics, some people think that space is actually quantized, so it comes in little segments that can't be divided further, right? Hilbert's claim might be empirically false, right? His geometry might not be true of the world, right? But all that goes to show is a space is different from the real numbers, right? If there is a similarity, it might just be because numbers were invented partly to deal with problems in physical space, right? And so the structure of numbers actually kind of resembles the structure of space. Now, if you started with the cardinals and realized you needed further divisions, then you might have invented rational numbers and then the real numbers in order to deal with concrete problems in physical space. Another problem with calling Hilbert's geometry nominalistic is that it includes second-order axioms that quantify over sets of points. Now, we're getting a little far afield here, but I might as well cover it. So sets are abstract objects, right? If he's talking about sets, is that a problem? Well, Field says we could reinterpret Hilbert's theory for him. Instead of talking about sets, just talk about regions of space, right? That would be fine for nominalists. Nominalists, that's a physical thing, right? There are other problems about second-order logic. It's incomplete, right? But it is consistent, right? And that's all you need for the conservativeness part. So Field doesn't think any of that is a problem. Okay, so this is a slightly longer lecture, but we're getting towards the end here. So, so far Field he hasn't argued yet that science can be nominalized, right, or be done without numbers. He just argued that if we could, there would be no problem ascending to a mathematical theory, right? That doesn't mean that it has to be true, right? And he's also shown why mathematics can be useful, right, even if it's not true, and it can be a nice supplement to a nominalist scientific theory, and it doesn't have to be true, right? So he's just sort of shown that this sort of thing is possible in principle. Now he's going to start to sketch what a physics without numbers would look like. So he talks a little bit about synthetic versus metric approaches here. So Hilbert's geometry is an example of a synthetic approach to geometry, right? So it defines relations without numbers and then maps them onto the real numbers later. A metric approach would use the numbers in the basic axioms of geometry. So obviously, he would prefer Hilbert's approach, the synthetic approach. But he thinks there's other reasons to prefer the synthetic approach when we're talking about physics, right? Which is if you use a synthetic approach and you don't talk about numbers, then you're only quantifying over things that have causal relations with each other. Numbers, even if you're a Platonist, you think numbers exist, they're in a non-spatiotemporal realm, right? They don't have any causal influence. And so it would be nice to formulate physics just in terms of the things that have causal relations with each other, right? And not bringing in non-causal, right, non-spatiotemporal entities like numbers, right? So, the gravitational constant is 6.67 times 10 to the 11. On the synthetic view, we would say we wouldn't think that number doesn't feature in the basic law, right? What we're really talking about is a causal relation, right? A force. That can be mapped onto this particular number if we want, right? But we could use another system. There's nothing essential about using the real numbers. If you wanted, you could use the real numbers multiplied by 2. It would preserve all the same relations. The reason we use the real numbers is because they're very useful, right? And they were designed deliberately to deal with these kinds of problems, right? These kinds of calculations. But in principle, you could use some other system as well. So he says, don't bake the numbers into your theory, right? Just keep your theory talking about the causal relation, the things that are related to each other. Numbers don't cause the moon to rotate around the Earth. Okay, so I'm just going to give a little glimpse of how you could. He starts by nominalizing Newtonian physics, right? Newtonian space. So we already have a geometry, right, that doesn't mention numbers, but it does have space-time points, distances, and things like that, regions of space. And Field says, great, those are fine, right? You can map them onto numbers if you want to, but you don't have to. That's fine, right? So now, here's just one example of a law, right, of physics. The acceleration of gravity, right, near the Earth is 9.81 meters per second squared. Okay, how would we do that without numbers, right? Well, all that's saying is that gravity will move objects across space and time in a particular relation, right? So all you have to do is define an interval of space. You can take the standard meter in France. So in France, there is an actual sort of rod that is the meter, right? And so we can say something congruent with that object, right? And that's a meter. And then concatenate that 9 times. Of course, now I just use the word 9. So actually what you would say is, right, interval of space, right, congruent with the standard meter in France, concatenated with itself, 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 concatenated blah, 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 right, 9 times. So now you have 9 meters. That's how you say 9 meters. It's really clunky, right, but you didn't use the number 9. Now to get the decimals, right, to get the 0.81, it's even more complicated because basically you have to have 81 line segments, each of which, if it was concatenated with itself 100 times, it would be congruent with the standard meter, right? Say that all without using the word 100, but you'd have to say concatenated with itself a lot of times, right? Similar process for intervals. So we've just defined, intervals of space, right? We basically said 9.81 meters without saying any numbers. You could do the same thing with time, right? So there's no standard meter, but it could be, how long it takes a clock hand to move across a given, something like that. That could be the interval you define. Now acceleration, right, so that would give us velocity, right? If you said, right, however, whatever distance it takes, whatever distance is traversed, right, given a distance of a clock that's traversed right at the same time. Get acceleration, you then have to say that relation over time again, right? But in principle, there's no problem with that either. You could define it all in terms of regions of space and the movement of a clock hand over the face of a clock. You can say all that stuff. You can imagine how incredibly clunky it is, right? But you don't need numbers to do it. Just talk about this stuff that exists. Gravity exists, intervals of space exist, intervals of time exist, and numbers make talking about all those relations among those things much, much easier, but they don't have to exist for us to do that. And that was Field's point, right? So we can accept Quine's criterion and say, yes, we are committed to things, the singular terms in our statements that we believe to be true. And we can believe in science to be true without believing in numbers because we can formulate science in a way where numbers do not appear as singular terms.